Last week when we left off, I hinted at this concept of equivalent capacitance, and I just want to remind us why we came up with the conclusion that for capacitors in series, they're going to have the same amount of Q, but a different voltage drop. And the way I explain that is we took like 3 sample capacitors in a series, and I said, like, this one is ginormous. It could hold like 500 charges on it, and this one could only hold 5. And then we looked at this and we thought, okay, so electrons are going to come, they're going to come this way, and so I'm going to have this buildup of negative charge. And based on the geometry of the capacitors, how much charge I can get on there. Because remember, the attractive nature of this polarized plate, so the electrons are going to flee from this plate and go to the next, and then build up charge here. And then the same thing is going to kind of keep happening because of that polarization. So I'll get electrons coming this way, and they'll start building up here. Once a plate has filled, so it's taken the most amount of charge that it can handle while balancing the attractive and repulsive nature of each, then that means I can't get any flow. So say this 5Q is full, it's going to exert a force from those electrons, the repulsive force between the electrons, and I can't get anything else coming this way, because this is just going to be like a stop everything. The motion is done, and my one smallest capacitor is fully full, or fully filled. So then we said that means that like the most that we can get on one, no matter how much it could actually hold based on its geometry, is going to be contingent on the smallest. And then we said, well, the potential difference is going to be different. And let's think about how we define capacitance. We said capacitance is going to be the amount of charge it can hold divided by the potential difference of those plates. And I said, so we can rewrite that V equals Q over C. And then I reminded you that capacitance is a fixed quantity. This is based on the geometry of our capacitors. So that's not changing. If this changes then, and they're all different size capacitors, then that means my potential difference is going to be different, just dependent on the amount of charge. So what that means for us is that if I want to know how much charge can actually be held for this system, I need to define this thing we call equivalent capacitance. Now, for capacitors in parallel, the way we define that equivalent capacitance is this 1 over CQ is going to be 1 over C1 plus 1 over C2, so on and so forth. It's just however many capacitors you have in a line. And we defined this being in a line, no other options of where to go as being in series. So for my example here, I have these 3 capacitors. I'm just reminding you, pico is 10 to the negative 12. I have these 3 capacitors, and I am going to put them in series in order to figure out how much charge I can get in this circuit. What I need to do is add up all of these capacitors. So I'll have 30 times 10 to the negative 12 plus 1 over 20 times 10 to the negative 12 plus 1 over 10 times 10 to the negative 12. Now, one of the things I can do to make my life easier is I can go 1 over CEQ. Remember, we're all about cutting down on the button pushing. This 10 to the negative 12 is going to pop up top. So is this one. So is this one. 10 to the negative 12 on the top is just 10 to the 12th. And when I do my math, I'm going to have 1 over 30 plus 1 over 20 plus 1 over 10. You can do the common denominator of that, but what I would say, oops, dropped my plus, is just go ahead and put that into your calculator. Now is just a fine time to go ahead and do that. You're not going to benefit from doing this symbolically. And then once I'm done, I get like 1 over CEQ is this huge number, the last thing I want to do after I add up all those things is to take the inverse, because what I want is this final answer to be like this CEQ. So I'm taking the inverse of it. That tells me I'm expecting a value around 10 to the negative 12, right? Because I'm flipping it, so I end up with that negative popping back out. And that's how I can check to make sure that my button pushing didn't go awry. So I'll end up with 5.45 times 10 to the negative 12 farads, or 5.45 picofarads. Okay, so now we have the equivalent capacitance. So our strategy here, our first step, is we want to simplify the entire circuit. So if you have a bunch of things in line, go ahead and combine them as this 1 over, and that will give you, now we have this battery that looks like this, the system that looks like this one line coming out here, and now we have a single capacitor. That is how much charge can flow through this system before it just stops. So what I want to do is use my voltage source. This would be my source. Need an E there. And this would be my CEQ, my equivalent capacitor. That will let me solve for my charge. So remember, we defined our capacitance equals Q over V. So capacitance times my voltage from the source will equal the amount of charge that can go on the system. Okay, so now we just button push that. What is my source? I don't think this gave it to me. Oh, 9 volt. So I will have 5.45 times 10 to the negative 12 farads times my voltage source of 9 volts. And that's going to give me 49 picocoulombs, if you will, or 10 to the negative 12 coulombs, is the amount of charge. So that's the amount of charge that I can get across each of these plates. So this system would be something like this. There's my battery start. I have 1, 2, 3. Notice this is just ever so slightly smaller than our largest capacitor. Excuse me. This is how much charge. That's not the capacitance. I said that, my mind just went, no. What did you just say? Because 49 is definitely larger than my smallest capacitor, right? I'm looking at the amount of charge here. This is coulombs. So here is my equivalent capacitance. And it is smaller than our smallest capacitor, and for reasons that we might be able to get into later on. But just kind of keep that in mind as your double check. All right, so we can get that much charge. And what's the question? What is the charge on each capacitor? We have answered that. 49 picocoulombs. Now, if I want to know the voltage drop across each, now I would take this thing and redraw, make it, there we go. Make it all of my individual capacitors again. And now I want the voltage drop across each, so I just rewrite that equation. That voltage drop is going to be the amount of charge, so this answer here, it's going to be the same for all, divided by the capacitance of each. So in this particular case, let me just take the 10 to the negative 12, or the voltage is going to be the Q. I'm sorry, my dog is having a little bit of an issue here. 49 times 10 to the negative 12 coulombs. That's the charge on the capacitor divided by the capacitance. So what do I have? I'll just choose the 10. So 10 times 10 to the negative 12. And that's in farads. These guys cancel out. 49 divided by 10 is going to give me 4.9 volts. So that's going to be the potential difference there. And I can do the same thing then for my 20 and my 30. 10 to the negative 12 divided by 20 times 10 to the negative 12. It's going to be a little over 2. 49 divided by 20. Yes, I know it's 49 divided by 20. Calculator, you're not helpful. So this is 2.45 volts. And then finally, our biggest capacitor is that 30 microfarads. So 49 times 10 to the negative 12 divided by 30 times 10 to the negative 12. It's going to be slightly larger than 1. So 49 divided by 30, 1.63. Now the only reason I went ahead with that little routine is to make sure that I emphasize something that's very important. We know that the voltage drop total across this thing was 9 volts. That was given in the problem. There we go, 9-volt battery supply. We used that quantity here to figure out how much charge. Whoops. So once we've done that, now we've figured out the voltage drop. And remember, the one thing I was talking about is something is going over all of its components, that by conservation of energy, what I have in the beginning is going to be lost going around the loop. So in the end, I should end up with no potential. My lake has filled up and is even with the waterfall, and all is good. And so I can just kind of add these numbers up, and if I'm not close to 9, that tells me that I made a mistake. She's having a bad day. And I get something like 8.98. Not exactly 9, but that's just going to be from rounding. So then I say, okay, I'm good. Now for the next one, let's come back and look at these in parallel.